Hello there and welcome to the Dreamy Ocean Channel. As you settle into this quiet moment, allow the gentle warmth of your breath to fill you, letting your shoulders softly drop and any lingering thoughts to drift away like leaves on a slow-moving stream carried by an unseen current. Unclench your jaw, release the gentle tension from your brow, and feel your body grow heavy, rooted, yet buoyant. How can a world so vast, so profoundly ancient, and so intimately connected to our own existence remain so utterly unknown? Its deepest chambers echoing with questions we cannot answer. Beneath the calm, shimmering surfaces of our planet's oceans in realms untouched by sunlight, there lie unseen forces that sing, groan and rumble, leaving even the most seasoned scientists to ponder their mysterious origins. We speak of sounds like the Bloop, Julia and Upsweep, official NOAA recordings that reveal a sonic landscape far stranger and more profound than we often imagine. Tonight, we will journey into those immense dark waters where the unheard becomes audible and the unknown begins to whisper its secrets. Let your consciousness float gently into these deep, dreaming waters. The silent depths and the whispers within. Far beneath the sun-kissed surface where the last golden rays of light surrender to an ever-deepening azure, lies a realm that humanity once perceived as the ultimate frontier of silence. A vast, crushing darkness stretching for miles in every direction where the very concept of sound seemed utterly alien, swallowed whole by the immense, unyielding pressure of the water column above. For countless millennia, our imagination painted the abyssal plains and the deepest trenches as tranquil, motionless voids, undisturbed by the clamor of the world above. A place where only the faintest, most ephemeral whispers of life might stir unheard and unseen. Yet this perception, born of our terrestrial experience, could not have been further from the profound, vibrating truth of this liquid world. For within the ocean's embrace, the physics of sound undergo a remarkable transformation, rendering the deep not silent, but a dynamic, resonating chamber. A vast, complex acoustic environment where vibrations travel with an efficiency that far surpasses their journey through the air we breathe. The very molecules of the ocean, packed so closely together, offer an almost frictionless pathway for these vibrations, allowing sound waves to propagate with astonishing speed, nearly 5 times faster than their journey through the thin, airy medium above, carrying their messages across immense distances from one side of an ocean basin to another with astonishing clarity. Imagine, if you will, a single distant thunderclap, its raw power dissipated quickly in the atmosphere. Yet if that same energy were unleashed beneath the waves, its rumble would course through the water for thousands of miles. A deep, resonant hum felt by creatures and instruments alike, a testament to the ocean's unparalleled capacity as a conductor of sound. As we gently descend into these profound depths, leaving behind the familiar warmth and light, a profound transformation begins to unfold around us. The vibrant spectrum of colors so essential to our surface world slowly fades first, the reds, then the oranges, until only the deepest blues and purples persist, eventually yielding to an absolute inky blackness. With each passing meter, the pressure mounts, an invisible, omnipresent force that reshapes the very fabric of existence, sculpting life into forms unseen on land, compressing water into a denser, colder state. Here in this eternal night, where sunlight has never touched the ocean floor, life finds its energy not from the sun, but from chemosynthesis, from the very chemical reactions bubbling forth from the Earth's core, creating oases of vibrant alien ecosystems around hydrothermal vents, their plumes rising like ghostly chimneys into the dark. It is within this extreme, often alien landscape, a world of crushing pressures and perpetual twilight, that the hidden symphony of the ocean truly begins to reveal itself. A complex tapestry woven from the whispers of currents, the groans of tectonic plates, and the calls of creatures adapted to this extraordinary, unforgiving environment. The ocean floor, far from being a static, silent bed, is a dynamic canvas of geological activity constantly shifting and reshaping under the immense forces of our planet. Deep within the Earth's crust, molten rock churns and flows, driving the movement of colossal tectonic plates, whose slow, inexorable grind against one another generates a continuous chorus of low-frequency sounds. Submarine earthquakes, far more frequent than their terrestrial counterparts, unleash powerful seismic waves that ripple through the water. Their deep, rumbling vibrations capable of traversing entire ocean basins. A colossal tremor felt by the very bedrock of the seafloor. Volcanic eruptions hidden beneath miles of water erupt with explosive force, sending plumes of superheated water and ash into the abyss, accompanied by sudden, violent bursts of sound that resonate through the water, a raw, primal roar emanating from the Earth's core. Hydrothermal vents, those deep-sea geysers spewing mineral-rich superheated water from cracks in the Earth's crust, contribute their own unique acoustic signature, a continuous, powerful hiss and gurgle like a giant, unseen boiler. Perpetually at work, a constant, energetic whisper that fuels the strange life forms congregating around these vibrant, isolated ecosystems. These geological sound events, though often imperceptible to our surface-dwelling senses, are fundamental components of the deep ocean's natural soundtrack, a constant reminder of the planet's restless living core. Beyond the deep geological murmurs, the very physical processes of the ocean itself generate a constant, pervasive background hum, an ambient soundscape that is never truly silent. The ceaseless motion of water, driven by planetary rotation, lunar gravity, and thermal differences, creates vast, slow-moving currents, like immense underwater rivers flowing across the abyssal plains and through deep ocean channels. These currents, as they encounter seamounts, ridges, and canyons, generate subtle, low-frequency turbulence and eddies, creating a continuous whispering rush, a gentle, pervasive swish that speaks of the ocean's ceaseless journey. On the surface, the relentless churning of waves driven by winds, sweeping across vast expanses of water, creates a broad spectrum of noise, from the gentle lapping against a shore to the thunderous crashes of storm-driven breakers, their energy transferring downwards, gradually diminishing, but still audible even in moderate depths. The rhythmic patter of rain falling upon the ocean's surface creates a distinctive broadband. Crackle a million tiny impacts, sending microscopic pressure waves cascading into the water column, a soft, ethereal hiss that permeates the upper layers. And in the polar regions, the majestic, slow-motion ballet of icebergs carving from glaciers, or the grinding, groaning movement of massive ice sheets, produces some of the most powerful natural sounds in the ocean. A series of deep, resonant cracks, pops, and prolonged, mournful moans that can travel for hundreds, even thousands of miles, a chilling primeval symphony of ice and water, echoing through the frigid, dark waters. Yet perhaps the most diverse and captivating element of the ocean's natural acoustic environment is the vibrant, often astonishing chorus generated by its countless inhabitants. From the microscopic plankton, whose collective movements can create subtle turbulence, to the colossal whales whose voices resonate across entire ocean basins, marine life communicates, hunts, navigates, and mates through an intricate language of sound. The clicks and whistles of dolphins and porpoises, sharp and precise, paint a detailed sonic picture of their surroundings, allowing them to hunt and navigate in the dimmest light. The haunting, complex songs of humpback whales evolving over years and shared across populations are vast operatic compositions, their low-frequency moans and groans carrying messages of immense distance and profound meaning, a true vocal masterpiece of the deep. Even seemingly silent fish through specialized swim bladders and muscular contractions produce a diverse array of grunts, croaks, chirps and drumming sounds forming intricate acoustic communities in coral reefs and spawning grounds, a constant chattering background hum that speaks of life's tireless activity. Invertebrates too contribute to this grand underwater orchestra. Snapping shrimp, for example, create a pervasive crackling soundscape with their rapidly closing claws, a constant static that can dominate the acoustic environment in some coastal areas, a tiny yet powerful contributor to the ocean's sonic palette. Each species, each individual adds its unique note to this immense living symphony, a constant, vibrant hum that tells the story of life thriving in the depths. For humanity, our understanding of this intricate underwater world began to expand significantly with the advent of specialized listening devices, instruments capable of translating the subtle pressure waves of the ocean into electrical signals our ears could comprehend. Early hydrophones, rudimentary by today's standards nonetheless, opened a window into a previously unimagined sonic landscape. They revealed that the ocean, far from being silent, was a realm of constant, pervasive sound, a complex interplay of natural phenomena and biological communication. This initial glimpse, however, was merely a prelude, a gentle introduction to the true complexity, and indeed the profound mysteries that awaited discovery. As our technology advanced, our ability to listen, to truly hear, the deep ocean grew exponentially. We began to differentiate between the familiar sounds of geological activity, the predictable patterns of marine life, and the ambient hum of physical processes. But even as our tools grew more sensitive, more sophisticated, and our understanding deepened, there remained, and indeed continue to remain, certain acoustic anomalies, sounds that defy easy categorization, signals that resonate through the deep without an identifiable source. These are the whispers from the unknown, the echoes of a mystery that lingers beneath the surface of our scientific comprehension, challenging our assumptions and inviting us to ponder what else might stir in the vast, unlit expanses of our planet's greatest wilderness. It is within this rich, dynamic, and often bewildering acoustic environment, against this backdrop of known geological rumblings and biological choruses, that the truly enigmatic sounds, the unexplained voices of the deep, begin to emerge, beckoning us closer to their silent, profound secrets, drawing us deeper into the heart of the ocean's enduring mystery. The stage is set, the deep waters are listening, and the unseen currents of sound are ready to carry us further into the realm of the unheard. The hydrophone network, the whispers from the unknown, those enigmatic echoes of the deep began to truly reveal themselves only when humanity developed the capacity to listen with an unprecedented sensitivity, to extend our ears into the very heart of the abyssal realm. This profound shift from passive observation to active acoustic exploration was catalyzed by the invention and subsequent refinement of the hydrophone, a device born from a fundamental understanding of how sound behaves in water, a technological marvel that transformed our perception of the ocean from a silent void into a vibrant, resonant chamber. At its core, a hydrophone is an underwater microphone, yet its function extends far beyond mere sound capture. Imagine, if you will, a delicate yet immensely resilient ear, crafted from specialized materials designed to withstand the crushing pressures and corrosive embrace of the deep ocean. This ear patiently awaits the subtle pressure fluctuations that ripple through the liquid medium, much like invisible waves on an unseen pond. When a sound wave, whether a distant whale's lament, the deep rumble of an underwater earthquake, or the mysterious groans from unknown sources, reaches its sensitive surface, it exerts a tiny, imperceptible force. This force, this momentary compression and rarefaction of water molecules, is then meticulously converted into an electrical signal, a language that our instruments can understand, analyze, and ultimately translate back into audible sound for the human ear. The scientific principle underpinning this remarkable conversion is often rooted in piezoelectricity, a fascinating property exhibited by certain crystals and ceramic materials. Picture these microscopic structures within the hydrophone arranged with meticulous precision. When mechanical stress, such as the pressure exerted by a passing sound wave, deforms these materials even minutely, they generate a tiny electrical voltage. Conversely, applying an electrical current to them causes them to change shape, a property utilized in sonar transducers to emit sound. In the hydrophone's receiving role, this generated voltage is directly proportional to the intensity of the incoming sound wave. A faint whisper from the deep produces a minuscule voltage, while a powerful booming resonance creates a more significant electrical pulse. This fragile electrical whisper is then amplified, filtered, and processed, allowing scientists to not only hear the sound, but to also dissect its characteristics, its frequency, its amplitude, its duration, and even through sophisticated triangulation, its point of origin. The journey of underwater listening from rudimentary beginnings to sophisticated global networks spans more than a century. Early attempts, often spurred by the harrowing experiences of naval warfare and the critical need to detect submerged vessels, involved simplistic devices lowered from ships, offering only fleeting glimpses into the ocean's acoustic landscape. These pioneering efforts, while limited in scope and sensitivity, undeniably proved that the deep was alive with sound, laying the foundational understanding for what was to come. The true revolution in deep ocean acoustics, however, emerged from the crucible of the Cold War. As the clandestine movements of submarines became a paramount concern for national security, the necessity arose for a vast, persistent, and highly sensitive listening capability that could monitor immense swaths of the ocean with unwavering vigilance. This imperative gave birth to the Sound Surveillance System, or SOSUS, a colossal, secretly developed network of hydrophone arrays strategically positioned across the Atlantic and Pacific Ocean basins. Envision strands of incredibly robust armored cable thicker than a human arm, stretching for hundreds, even thousands of miles across the abyssal plains, snaking their way over seamounts and into the deepest trenches. Along these immense underwater arteries, like pearls on a colossal necklace, were arrayed hundreds, perhaps thousands of individual hydrophones, each meticulously calibrated and designed to function flawlessly under unimaginable pressures and in perpetual darkness. These arrays were not merely isolated listening posts. They were interconnected, forming vast distributed ears capable of detecting and localizing even the faintest acoustic signatures emanating from submerged objects. The deployment of SOSUS was an engineering marvel of its time, a testament to human ingenuity and perseverance. Specialized cable-laying ships equipped with immense spools of optical fiber and copper conductors meticulously navigated pre-surveyed routes, slowly paying out the heavy, resilient cable onto the ocean floor. The hydrophones themselves were encased in pressure-resistant housings, often made of titanium or specialized alloys capable of withstanding pressures that would crush a conventional submarine instantly. Each hydrophone within an array was precisely spaced, forming geometric patterns that allowed for sophisticated beam-forming techniques. By analyzing the minute differences in the arrival time of a sound wave at multiple hydrophones, scientists could effectively steer their acoustic beam, focusing their listening power in a specific direction and pinpointing the source of a sound with remarkable accuracy, much like how our two ears allow us to localize sounds in the air. The data streams generated by these vast hydrophone networks were immense, a continuous torrent of acoustic information flowing back to shore-based processing centers. Here, sophisticated computer algorithms and highly trained human operators worked tirelessly, sifting through the ceaseless cacophony of the ocean. They were searching for anomalies, for the distinctive propeller cavitation of a submarine, the unique engine hum, or the faint telltale clicks of sonar. The sheer volume of data, however, also meant that countless other sounds, the natural symphony of the ocean, were inadvertently captured. These included the majestic songs of whales, the deep rumbling of earthquakes, the crackle of distant ice, and as we would later discover, sounds that defied immediate explanation. For decades, the existence and capabilities of SOSUS remained one of the most closely guarded secrets of the Cold War. Its primary mission was singular: to detect and track Soviet submarines, providing a crucial early warning system against potential threats. However, with the geopolitical landscape shifting dramatically in the late 20th century, the strategic imperative for such absolute secrecy began to wane. In a landmark decision, parts of the SOSUS network, specifically those areas deemed less critical for national security, were declassified and opened up to scientific research. This pivotal moment marked a new era for oceanography and marine biology, transforming instruments of military surveillance into tools of profound scientific discovery. Suddenly, oceanographers, seismologists, and marine biologists gained access to an unparalleled archive of deep ocean acoustic data, a continuous long-term record spanning decades and covering vast geographical areas. This declassification was akin to suddenly being granted a key to a secret library filled with untold stories of the deep. Researchers could now analyze the low-frequency vocalizations of baleen whales, tracing their migratory paths and understanding their communication patterns in unprecedented detail. Seismologists could monitor submarine earthquakes and volcanic eruptions with greater precision, gaining new insights into the Earth's restless geological processes. And, perhaps most intriguingly, they began to encounter a series of powerful, enigmatic sounds, distinct from any known biological or geological source sounds, that resonated with an intensity and a spectral signature that defied conventional explanation. The challenges of maintaining and operating such an extensive network in the deep ocean are formidable. The environment itself is relentlessly hostile. The immense pressure at depths of several miles can instantly crush unprotected equipment, demanding materials of extraordinary strength and resilience. The corrosive effects of salt water, combined with the presence of marine organisms that can foul sensors or even damage cables, necessitate robust engineering and continuous monitoring. Powering these remote hydrophone arrays requires long-life batteries, or more commonly power transmitted along the same cables that carry the acoustic data, a complex feat of electrical engineering over vast distances. Despite these monumental challenges, the hydrophone networks continue to operate, a testament to the dedication of engineers and scientists who brave the complexities of the deep to extend humanity's senses into this alien frontier. As these networks continue to evolve, incorporating newer technologies like autonomous underwater vehicles, AUVs equipped with hydrophones, and integrating with global observatories, our ability to listen to the ocean's hidden symphony grows ever more refined. Yet even with all our technological prowess, the ocean retains its capacity for mystery, for producing sounds that whisper of forces or entities beyond our current understanding. The hydrophone network, once a silent sentinel of the Cold War, has become a global ear, listening not just for threats but for the profound, often inexplicable secrets that the vast dark waters continue to hold patiently, waiting for us to decipher their deepest, most resonant truths. It is through these incredible listening devices that the stage was truly set for the discovery of the Bloop, Julia upsweep, and other sounds that continue to challenge our understanding of the deep, drawing us ever deeper into the ocean's enduring enigma. A new era of oceanic listening. As the mid-20th century unfolded, casting long, uncertain shadows across the global stage, a profound shift began to reshape humanity's relationship with the ocean. The era known as the Cold War, a period of intense ideological and geopolitical rivalry, was not merely fought on land or in the skies. Its most clandestine and strategically critical battles were often waged in the deep, silent realm beneath the waves. Here, in the crushing darkness, the stealthy movements of submarines, those sleek metallic leviathans, became a paramount concern, representing a silent, unseen threat that could emerge from the depths with devastating speed and anonymity. The very existence of these submerged vessels, capable of carrying immense destructive power and disappearing without a trace, ignited an urgent, almost desperate need to pierce the ocean's opaque curtain, to hear what could not be seen, and to track what could not be found by conventional means. This profound imperative, born of global tensions and the chilling spectre of nuclear conflict, ultimately ushered in a new, unprecedented era of oceanic listening, forever changing our understanding of the deep. The genesis of the sound surveillance system, universally known as SOSUS, was a direct response to this escalating strategic challenge. Imagine the minds of brilliant engineers and scientists working in the deepest secrecy, grappling with an almost insurmountable problem: how to detect and continuously monitor objects moving silently through a medium as vast and complex as the ocean across distances spanning thousands of miles. The solution, audacious in its conception and monumental in its execution, was to transform the entire ocean basin into a colossal listening device, a distributed network of ultra-sensitive hydrophones designed to pick up the faintest whispers of a distant submarine. The goal was not merely to detect, it was to localize, to track, and to understand the acoustic signatures of these elusive underwater craft, providing a continuous real-time picture of their movements, a strategic advantage of immeasurable value in a world teetering on the edge of uncertainty. The construction and deployment of SOSUS represent one of the most remarkable feats of underwater engineering in human history, shrouded for decades in impenetrable secrecy. Picture vast fleets of specialized cable-laying ships, their decks laden with immense heavy spools of armored cable, each meticulously designed to house optical fibers for data transmission and copper conductors for power. These vessels embarked on arduous clandestine voyages, slowly paying out thousands of miles of these resilient cables onto the abyssal plains, carefully navigating intricate underwater topographies, avoiding seamounts, trenches, and volcanic ridges. Along these submerged arteries, at precisely calculated intervals, were attached the hydrophone arrays themselves. Clusters of multiple hydrophones, each encased in robust, pressure-resistant housings, meticulously calibrated to function flawlessly under the immense pressures found at depths of several miles. These individual hydrophones, often employing advanced piezoelectric ceramics, were designed to be extraordinarily sensitive, capable of detecting minute pressure fluctuations that would signify the presence of a distant vessel even against the pervasive background noise of the ocean. The sheer scale of the SOSUS project was staggering. These vast arrays were strategically positioned at critical choke points and across wide ocean expanses, forming an invisible acoustic fence designed to monitor the movements of submarines entering or traversing key strategic areas. The data, a continuous high-bandwidth stream of acoustic information, flowed tirelessly through the underwater cables, traversing thousands of kilometers of ocean floor before emerging at highly classified shore-based facilities. These facilities, often nestled in remote coastal locations, were veritable nerve centers teeming with sophisticated electronic equipment and staffed by highly trained acoustic analysts. These individuals, often naval personnel with specialized expertise, spent their shifts in dimly lit rooms, meticulously sifting through the ceaseless torrent of oceanic sound, their ears and minds finely tuned to discern the subtle, telltale signatures of a submarine's propeller cavitation, its unique engine hum, or the faint, rhythmic pings of its active sonar. It was a silent, relentless watch, a continuous vigil maintained around the clock, year after year, forming a critical, invisible shield during the most tense periods of the Cold War. Throughout its decades of clandestine operation, the SOSUS network, while primarily focused on military objectives, inadvertently became the world's most comprehensive and long-duration deep ocean acoustic observatory. The hydrophones, designed to be exquisitely sensitive to any sound naturally captured, not only the faint mechanical hums of distant submarines, but also the entire symphony of the natural ocean. Early on, these non-military sounds, the songs of whales, the rumbles of distant earthquakes, the crackle of ice, the whisper of currents, were often treated as background noise distractions to be filtered out, or at best noted as curious anomalies. While some astute military analysts undoubtedly recognize the patterns of marine life or geological activity, the primary mission demanded that these natural phenomena remain secondary to the urgent task of national security. Yet even in this context of military secrecy, the sheer volume and continuous nature of the data were slowly building an unparalleled archive, a hidden record of the ocean's true acoustic character, waiting for a future generation of scientists to unlock its secrets. The geopolitical landscape, however, is ever shifting. As the Cold War gradually drew to a close in the late 1980s and early 1990s, the intense strategic imperative for absolute secrecy surrounding SOSUS began to wane. The easing of global tensions, the dissolution of the Soviet Union, and a broader shift in international relations created an opportunity for a remarkable transition. In a landmark decision that would profoundly impact oceanographic research parts of the SOSUS network, specifically those arrays deemed less critical for ongoing military surveillance, were declassified and made accessible to the scientific community. This pivotal moment marked a true new era, a transformation of instruments of silent military vigilance into powerful tools for profound scientific discovery, turning swords, metaphorically speaking, into plowshares for the exploration of the deep. The impact of this declassification on oceanography, marine biology, and seismology was nothing short of revolutionary. Suddenly, academic researchers who had previously been limited to short-term localized acoustic surveys gained access to an unprecedented, continuous, and geographically expansive dataset. This was not merely a collection of isolated recordings. It was a vast, multi-decadal acoustic archive, a continuous ear on the deep ocean, listening without interruption for years on end. Scientists could now analyze the low-frequency vocalizations of baleen whales, tracing their epic migratory paths across entire ocean basins, understanding their intricate communication patterns, and monitoring the long-term health and distribution of populations with a clarity and scale previously unimaginable. Seismologists gained an unparalleled network for detecting and localizing submarine earthquakes and volcanic eruptions, providing invaluable insights into tectonic plate movements, seafloor spreading, and the Earth's restless geological processes that are largely hidden beneath the waves. Oceanographers could study the acoustic signatures of deep ocean currents, internal waves, and the subtle interactions between the water column and the seafloor, unraveling the complex dynamics of this immense fluid system. Within this vast new dataset, a treasure trove of information about the natural world, something else began to emerge, something distinct and profoundly intriguing. As scientists meticulously sifted through the years of recordings, applying their specialized knowledge to filter out known biological calls and geological rumbles, they started to identify powerful low-frequency sounds that defied immediate categorization. These were not the familiar songs of whales, nor the distinct tremors of earthquakes, nor the crackle of ice. These were acoustic anomalies, signals that resonated with an intensity and a spectral signature that seemed alien, unexplained by any known natural or anthropogenic source. The very sensitivity and continuous nature of the SOSUS network, designed to capture everything for military purposes, had inadvertently captured these enigmatic whispers from the unknown, these profound mysteries embedded within the ocean's acoustic fabric. The legacy of the Cold War, therefore, extends far beyond geopolitical shifts. It has irrevocably shaped our understanding of the deep ocean. What was once a clandestine network dedicated to silent vigilance has evolved into an invaluable scientific observatory, its echoes continuing to resonate through the corridors of research institutions worldwide. The insights gleaned from these declassified hydrophone arrays have fundamentally advanced our knowledge of marine ecosystems, geological processes, and the very physics of sound in water. Yet even with all our accumulated knowledge and technological prowess, the ocean retains its profound capacity for mystery. It is precisely within this context, this transition from military secrecy to scientific openness, and within the vast continuous acoustic record provided by the SOSUS network, that the most compelling and genuinely unexplained sounds from the ocean floor, the Bloop, Julia Upsweep and others, first made their enigmatic presence known, beckoning us further into the heart of the deep, inviting us to ponder the unseen forces that still stir in its vast, dark embrace. The stage is now perfectly set for us to turn our attention to these specific, perplexing acoustic events, to listen closely to the voices that continue to challenge our understanding of the ocean's enduring secrets. A titanic roar from the deep. From the vast, continuous acoustic tapestry woven by the declassified hydrophone networks, a particular sound emerged in the late 1990s that would capture the scientific imagination and ripple through the public consciousness with an almost mythical resonance. It was a sound so powerful, so enigmatic, and so utterly unlike anything previously catalogued that it quickly earned its own evocative onomatopoeic name, the Bloop. This titanic roar from the deep, recorded across thousands of miles of ocean, presented a profound challenge to our understanding of the abyssal realm, pushing the boundaries of known marine biology and geology, and inviting a cascade of both scientific inquiry and speculative wonder. The Bloop made its dramatic debut in the summer of 1997, a precise moment in the ongoing vigil of the equatorial Pacific Ocean. The U.S. National Oceanic and Atmospheric Administration, or NOAA, specifically its Pacific Marine Environmental Laboratories Acoustic Monitoring Project, was operating a series of autonomous hydrophone arrays. These arrays, strategically deployed in deep ocean basins, were designed to listen for submarine volcanoes, seismic activity, and the low-frequency vocalizations of marine mammals. On multiple occasions during that pivotal year, these sensitive instruments spread across an astonishing range of approximately 5,000 kilometers, an expanse equivalent to the entire width of the continental United States, simultaneously detected an ultra-low frequency sound event of immense power. Imagine for a moment the sheer scale of this detection, a sound so potent that its pressure waves traveled across an entire ocean, reaching hydrophones separated by thousands of miles, yet still arriving with enough clarity and energy to be registered as a distinct, powerful signal. This was not a localized event, a faint whisper from a single point. This was a colossal acoustic phenomenon reverberating through the very fabric of the deep ocean basin. The signal itself was characterized by its rapid frequency variation, a characteristic rise and fall in pitch that gave it its distinctive bloop sound. It was an impulsive yet sustained event, lasting for about a minute, its low-frequency components dipping below 1 Hz, the very threshold of human hearing, yet imbued with an intensity that hinted at an extraordinary source. Upon initial analysis by NOAA scientists, several key characteristics of the bloop immediately stood out, setting it apart from any previously identified natural or anthropogenic sound. Firstly, its sheer amplitude was staggering. To be detected across such vast distances by multiple widely separated hydrophones, the source would have had to generate an acoustic power output, far exceeding that of even the largest known whales, such as the blue whale, whose calls are renowned for their ability to travel across entire ocean basins. A blue whale's vocalization, while incredibly powerful, is typically localized within a few hundred kilometers for clear detection. The bloop's reach was on an entirely different magnitude. This immense power immediately led researchers to consider only a handful of potential origins, colossal geological events, or something biological of an unimaginable scale. Secondly, the spectral signature of the bloop. Its unique pattern of frequencies and harmonics bore a distinct resemblance to that of a living creature, specifically the vocalizations of large baleen whales. This was not the sharp, percussive crack of an icequake, nor the broadband rumble of a submarine volcano. Instead, it possessed a biological-like quality, a waveform that hinted at an organic origin, a complex modulated sound that resonated with the characteristics of a living entity's communication. This biological resemblance, combined with its immense power, ignited a fervent discussion within the scientific community. Could there be an unknown colossal marine animal, far larger and more vocal than any we have ever discovered, lurking in the deepest, most unexplored regions of our planet's oceans? The location of the bloop's origin, triangulated by the multiple hydrophone detections, consistently pointed to a remote, utterly unexplored region of the South Pacific Ocean, approximately 50 degrees south latitude and 100 degrees west longitude. This area is characterized by immense depths far from major shipping lanes and largely untouched by human exploration. It is a realm of perpetual darkness, crushing pressures and cold, where the ocean floor remains largely unmapped, its mysteries preserved beneath miles of water. The remoteness of this location only added to the allure and the enigma of the bloop, suggesting that its source, whatever it might be, was a denizen of the truly wild, uncharted abyssal frontier. Initially, scientists considered various geological explanations for the bloop. Could it be a particularly powerful ice quake, the fracturing of a colossal iceberg? The Southern Ocean, with its vast ice sheets and calving glaciers, is a known source of powerful low-frequency sounds. However, while ice quakes can indeed be immensely powerful and travel vast distances, their acoustic signatures typically possess a sharp, brittle quality, a sudden, explosive release of energy followed by reverberation. The bloop, with its more sustained, modulated, and biological-like waveform, did not perfectly align with the established characteristics of ice-related sounds. Furthermore, while the general region is near an active ice front, the precise location of the bloop's source was not directly within the immediate vicinity of a major calving event. Another geological hypothesis centered on submarine volcanic activity or seismic events. The Pacific Ring of Fire, with its intense tectonic activity, is a known generator of powerful underwater sounds. But again, the spectral characteristics of volcanic eruptions or submarine earthquakes, while possessing immense power, tend to be broadband chaotic and lacking the distinct modulated quality observed in the bloop. The rapid frequency variation, the rise and fall in pitch, was a particularly challenging aspect for purely geological explanations to fully encompass. It was the biological hypothesis, therefore, that truly captivated researchers and the public alike. The idea of an unknown colossal creature, a leviathan of unimaginable size, vocalizing in the deep, resonated deeply with our primal sense of wonder and fear of the unknown. Scientists theorized that if such a creature existed, its immense body size would allow it to produce extremely low-frequency sounds, capable of traveling thousands of miles through the ocean's acoustic channel. Much like the great whales, but on an even grander scale. The logic was compelling. Larger animals tend to produce lower frequency sounds to communicate over greater distances, and the bloop's low-frequency biological-like signature, combined with its immense power, seemed to point towards something truly enormous. This line of thinking naturally led to questions about what kind of creature could possibly inhabit such depths and produce such a profound sound. Could it be a truly gigantic squid, or perhaps a species of whale far exceeding the size of the blue whale, or even something entirely new? A creature from the realm of cryptids and legends, finally making its presence known through sound. The bloop, however, was not a singular, isolated event that vanished without a trace. While the most famous recordings occurred in 1997, scientists have since revisited and analyzed other historical data searching for similar signatures. The initial discovery sparked a renewed scientific interest in the potential for undiscovered megafauna in the deep ocean fueling expeditions and further acoustic monitoring efforts. The very existence of the bloop served as a powerful reminder of how little we truly know about the vast majority of our planet, particularly its deepest, most inaccessible regions. It underscored the profound humility required when confronting the ocean's enduring mysteries, acknowledging that our current catalogue of life and geological processes might be far from complete. Years later, after extensive reanalysis of the original data and the acquisition of new acoustic information, NOAA scientists began to converge on a more refined explanation, one that, while perhaps less dramatic than a giant unknown creature, was nonetheless rooted in the immense dynamic forces of our planet. They eventually concluded that the bloop's characteristics, its ultra-low frequency, immense power, and biological-like spectrogram, were most consistent with the acoustic signature of a large ice quake, specifically the fracturing and carving of massive icebergs. The initial skepticism regarding ice quakes was largely based on the perceived biological-like nature of the sound. However, further research into the acoustics of massive ice fracturing revealed that these events can indeed produce incredibly complex modulated sounds, often with rapid frequency variations that mimic biological vocalizations. When immense blocks of ice, sometimes miles across fracture and carve from a glacier or an ice shelf, the sudden violent release of colossal amounts of stored energy generates powerful seismic and acoustic waves. These waves, traveling through both the ice and the water, can create a rich broadband acoustic signature with certain components resonating at extremely low frequencies and exhibiting the very blooping characteristic that defined the enigma. The sheer scale of such an event involving ice masses weighing billions of tons could easily account for the immense power required for the sound to be detected across thousands of kilometers. The location of the Bloop in the remote South Pacific is also consistent with regions where large icebergs drift and fracture, particularly around the Antarctic Peninsula and the Southern Ocean. While not directly adjacent to a glacier, large tabular icebergs can drift for thousands of miles, slowly breaking apart and generating powerful acoustic events far from their origin. The biological-like quality, therefore, was a fascinating acoustic mimicry, a testament to the complex ways in which raw geological forces can produce sounds that trick our analytical frameworks. Despite this scientific consensus, the initial mystery of the Bloop, its profound resonance with the idea of unknown leviathans, continues to linger in the public imagination. It remains a powerful symbol of the ocean's enduring capacity for wonder and the lure of the undiscovered. Even with a geological explanation, the Bloop serves as a potent reminder that the deep ocean is a realm of colossal, often breathtaking natural phenomena, forces that dwarf our human scale and produce sounds that can mimic the very breath of life itself. The journey into the ocean's acoustic mysteries, however, did not end with the Bloop. Other enigmatic voices, equally perplexing in their own right, continued to emerge from the deep, each carrying its own unique set of questions, drawing us deeper into the heart of the ocean's still unfolding sonic narrative. A lingering, spectral voice. As the echoes of the Bloop slowly began to settle into a more grounded, albeit still awe-inspiring geological explanation, the deep ocean continued its relentless acoustic vigil, and other enigmatic voices emerged from its vast, dark chambers. Among these, a particularly haunting and prolonged sound christened Julia revealed itself in 1999, presenting a new kind of puzzle. A lingering, spectral voice that resonated through the abyssal depths with a distinct, almost mournful quality. Unlike the sudden, powerful burst of the Bloop, Julia unfolded as a sustained broadband event lasting for an astonishing 15 minutes, its characteristics pointing to a different, yet equally profound mystery within the ocean's intricate sonic landscape. Julia was detected once again by the vigilant hydrophone arrays operated by NOAA's Pacific Marine Environmental Laboratory. These instruments, patiently listening across the vast expanse of the equatorial Pacific, registered the sound across an immense range, suggesting a source of considerable acoustic power. The location of its origin was pinpointed through meticulous triangulation to a region off the west coast of South America, near the equatorial Pacific, a dynamic area known for its complex interplay of ocean currents, tectonic activity, and diverse marine life. This geographical context, while offering some clues, did not immediately provide a clear explanation for the peculiar nature of Julia's lament. The most striking characteristic of Julia was its remarkable duration. A full 15 minutes of continuous broadband sound is an extraordinary event in the deep ocean. Most known biological vocalizations, even the complex songs of baleen whales, consist of repeated phrases and distinct calls, but rarely sustain a continuous, unmodulated sound for such an extended period. Similarly, typical geological events such as submarine earthquakes or volcanic eruptions tend to be more impulsive and transient, their primary energy dissipating relatively quickly, leaving behind only reverberations. Julia's sustained nature therefore immediately set it apart, demanding a different kind of explanation, one that could account for such a prolonged and powerful acoustic emission. Furthermore, the spectral analysis of Julia revealed a complex broadband signature. This means that the sound was not concentrated at a single, narrow frequency, but rather spread across a wide range of frequencies, encompassing both low and higher components. This broadband characteristic is often associated with chaotic or turbulent processes such as the breaking of waves, the movement of ice, or the turbulent flow of water. However, the specific quality of Julia's broadband signature, its lingering, almost wailing nature, did not perfectly align with typical ambient ocean noise or known biological choruses. Scientists described it as a train of sounds, a continuous flow rather than a series of distinct pulses, further deepening its enigmatic quality. The challenge presented by Julia was to identify a mechanism capable of generating such a powerful, sustained and broadband sound in the deep ocean. The immense duration immediately ruled out many potential sources. A single large animal, even an undiscovered leviathan, would struggle to produce a continuous vocalization for 15 minutes without pauses for respiration or physiological recovery. Similarly, a single isolated geological event like a submarine landslide or a small volcanic eruption would typically exhaust its primary energy far more rapidly. The sustained nature of Julia pointed towards a process that was either continuously energetic or involved a very large-scale, slow-moving phenomenon. One of the leading hypotheses, and the one that has gained significant traction among NOAA scientists, attributes Julia to the sounds generated by a very large iceberg running aground or scraping along the seafloor. Imagine a colossal mass of ice, perhaps several miles in length, slowly drifting across the vast ocean. As it encounters shallower waters or a submerged seamount or a continental shelf, its immense weight and inexorable momentum cause it to grind against the rocky substrate. This colossal friction, this slow, powerful abrasion of ice against rock, would generate a continuous broadband sound as the ice mass scrapes, shudders, and fractures under the immense stress. The sheer scale of such an event, involving billions of tons of ice in motion, could easily account for the sustained duration and the immense acoustic power detected by the hydrophones across thousands of miles. The spectral characteristics of Julia, with its broadband nature and continuous flow, are also highly consistent with the sounds produced by large-scale ice-grounding events. As ice rubs against rock, it creates a chaotic mixture of frequencies, a grinding, groaning, and scraping sound that would manifest as a broadband signal. The wailing quality described by some scientists could arise from the resonant frequencies generated as the massive ice structure flexes and vibrates under stress, akin to a colossal, slow-motion instrument being played by the forces of the ocean. Furthermore, the geographical location of Julia's detection in the equatorial Pacific is not immediately adjacent to major glacier fronts. However, it is well within the range where very large, persistent icebergs carved from the Antarctic ice sheet can drift for extended periods carried by deep ocean currents before eventually melting or running aground in unexpected locations. Another geological consideration, though less favored than the iceberg hypothesis, involved the possibility of a very large-scale, slow-motion submarine landslide. Imagine an immense mass of sediment, perhaps triggered by an underwater earthquake or the destabilization of a continental slope, slowly slumping down an abyssal canyon. the sheer volume of material in motion, the continuous grinding and churning of sediment and rock, could theoretically generate a sustained broadband acoustic signal. However, the precise spectral signature and the duration of Julia align more closely with the unique characteristics of ice grounding. Submarine landslides, while powerful, often have a more distinct initial trigger and a more chaotic, less wailing acoustic profile. The biological hypothesis, while perhaps less prominent for Julia than for the Bloop, was also briefly considered. Could a supercolony of unknown, extremely vocal deep-sea creatures be responsible for such a sustained sound? While some deep-sea organisms are known to produce continuous acoustic signals, the sheer power and duration of Julia would require an organism or a collective of organisms of truly unprecedented scale and acoustic output. The wailing quality, while evocative, did not perfectly match any known biological vocalization patterns, which tend to be more structured and repetitive. Therefore, the scientific consensus leaned away from a biological source for Julia, favoring the more geophysically plausible explanation of large-scale ice dynamics. The significance of Julia, even with its eventual, albeit still challenging explanation, lies in its contribution to our understanding of the ocean's natural soundscape. It highlighted the immense acoustic power generated by large-scale cryoseismic events, the fracturing and movement of ice, and demonstrated how these natural forces can produce sounds that are profoundly impactful, traveling across vast distances and mimicking in their complexity the very voices of life. It also underscored the fact that even seemingly known phenomena like icebergs can behave in acoustically complex and surprising ways when interacting with the deep ocean environment on a colossal scale. The study of Julia and other similar sounds has prompted oceanographers and glaciologists to develop more sophisticated models for understanding the acoustic signatures of ice. This includes not only the dramatic calving events, but also the more subtle yet powerful processes of ice grinding, creaking and fracturing as it interacts with the sea floor or other ice masses. These insights are becoming increasingly important in the context of global climate change as the dynamics of polar ice sheets and glacier melt accelerate, potentially leading to an increase in these powerful deep ocean acoustic events. So, while Julia's lament may not be the voice of an unknown leviathan, it is nonetheless the profound acoustic signature of a colossal natural force at work in the deep, dark ocean. It is the sound of ice, an immense patient sculptor of our planet, slowly, inexorably interacting with the ancient seafloor, creating a sustained, mournful groan that reverberates through the abyssal depths. It is a reminder that the ocean is a dynamic, ever-changing realm, full of immense, powerful processes that continue to shape our world, and whose acoustic signatures offer us a unique window into their silent, unseen mechanics. Julia therefore stands as a testament to the ocean's enduring capacity to surprise us, to challenge our assumptions, and to reveal the hidden, powerful music of our living planet, drawing us ever deeper into its rich, resonant, and still mysterious acoustic embrace. A deep ocean drone. As the deep ocean continued to yield its acoustic secrets, each new sound presenting a unique puzzle, another persistent, enigmatic voice began to emerge from the vast, dark waters, distinct from the impulsive burst of the Bloop and the sustained lament of Julia. This sound, christened upsweep, was characterized by its remarkably consistent narrow band and extraordinarily long-duration nature, a deep ocean drone that hummed through the abyssal depths. For decades, its presence, a constant, unwavering question mark in the global acoustic record. Discovered in the early 1990s by the same vigilant NOAA hydrophone arrays, upsweep presented a challenge rooted not in its sudden power, but in its relentless persistence and spectral purity, a testament to the ocean's capacity for subtle yet profound mysteries. Upsweep first caught the attention of acoustic analysts in 1991 as they meticulously reviewed the continuous streams of data flowing from the Pacific Marine Environmental Laboratory's autonomous hydrophone arrays. These instruments, strategically deployed across the vast expanse of the Pacific Ocean, consistently registered a peculiar low-frequency sound that seemed to emanate from a specific region. Unlike other transient signals, upsweep was a nearly continuous presence, a faint yet unmistakable hum that would rise in a frequency over several seconds, then repeat, creating a distinct upsweep pattern. This rhythmic, almost hypnotic oscillation, repeated over and over, day after day, year after year, made it uniquely identifiable amidst the ocean's ceaseless background noise. The primary characteristics of upsweep that immediately set it apart were its narrow band frequency, its consistent pattern, and its astonishingly long duration. Most natural ocean sounds, whether geological or biological, tend to be broadband, encompassing a wide range of frequencies, or are transient, appearing and disappearing with varying degrees of regularity. Upsweep, however, was concentrated within a very specific, narrow frequency band, typically peaking around 50 Hz, a low, guttural hum that resonated through the deep. Its pattern was remarkably consistent, a gradual, slow increase in frequency over a period of several seconds, followed by a slight pause, and then a repetition of the entire sequence. This distinctive upsweep pattern was not random. It was structured, almost deliberate in its repetition, and most remarkably, it was persistent. For nearly 2 decades from its initial detection in 1991 until its gradual fading in the early 2000s, upsweep was a near-constant feature in the deep Pacific acoustic record, a tireless, unseen drone operating deep beneath the waves. The location of upsweep's origin, triangulated by the multiple hydrophone detections, consistently pointed to a highly active seismic and volcanic region in the South Pacific, near the boundary of the Pacific and Antarctic plates. Specifically, it was localized to an area of active submarine volcanism and hydrothermal venting. This geographical context provided the first significant clues, directing scientists toward a geological explanation, a departure from the initial biological considerations that often accompany such powerful, unexplained sounds. The very consistency and narrow-band nature of upsweep suggested a stable, continuous energy source, something more akin to a geological process than a biological vocalization. Upon initial analysis, scientists considered various hypotheses to explain upsweep's unique characteristics. Could it be a new type of biological vocalization? While some marine mammals, particularly baleen whales, produce low-frequency sounds, their vocalizations tend to be more complex with varied patterns and durations, and typically do not maintain such a perfectly consistent narrow-band upsweep for decades. The sheer persistence and spectral purity of upsweep made a biological origin highly improbable, as even the most tireless vocalizer would eventually need to rest or vary its call. Could it be an anthropogenic sound, a byproduct of human activity? While shipping noise, sonar pings and other human-generated sounds are pervasive in the ocean, their signatures are generally well understood and do not typically exhibit the consistent narrow-band upsweep pattern observed for such an extended period. Furthermore, the remote location of its origin, far from major shipping lanes or known military operations, made an anthropogenic source highly unlikely. The most compelling hypotheses, therefore, began to converge around geological processes, specifically those related to submarine volcanism and hydrothermal activity. Imagine the immense forces at play deep beneath the ocean floor, where molten rocks superheated water and tectonic plates are in constant slow-motion interaction. Scientists theorized that upsweep could be generated by the continuous resonant vibration of magma moving through subterranean chambers beneath an active submarine volcano. As molten rock or magma flows through constricted conduits or resonates within subsurface cavities, it can create a continuous hum, a deep, sustained drone, much like the sound of water flowing through pipes, but on a colossal geological scale. The gradual upsweep in frequency could potentially be explained by subtle changes in pressure temperature or the geometry of these magma chambers as the molten material moves and shifts. Another strong geological candidate involved the continuous emission of superheated water from deep-sea hydrothermal vents. These vents, often found along mid-ocean ridges, spew plumes of mineral-rich, extremely hot water into the cold, dark abyss. The turbulent flow of this superheated water, as it rapidly mixes with the surrounding cold seawater, can generate a continuous, powerful acoustic signature. If a particularly large or sustained vent system, perhaps one with a unique geological structure, were to act as a resonant chamber, it could potentially produce the narrow-band, persistent hum of upsweep. The upsweep pattern itself might be related to fluctuations in the vent's output, changes in flow dynamics, or even the periodic release of gas bubbles from the vent system. The location of upsweep's origin precisely within a region known for active seafloor spreading and intense hydrothermal activity strongly supported these geological explanations. The Pacific Antarctic ridge, where upsweep was localized, is one of the fastest spreading mid-ocean ridges on Earth, a dynamic zone where new oceanic crust is continuously formed, accompanied by frequent submarine volcanic eruptions and the proliferation of hydrothermal vents. This environmental context provides a rich tapestry of geological processes capable of generating sustained, powerful, low-frequency sounds. The gradual fading of upsweep in the early 2000s further lent credence to a geological explanation. If the sound was indeed generated by a specific submarine volcanic or hydrothermal system, then a change in that system's activity, perhaps a shift in magma flow, a blockage in a vent, or a change in tectonic stress, could easily account for its eventual disappearance from the acoustic record. Unlike biological vocalizations, which might cease due to migration or population changes, a geological drone would likely fade or cease when the underlying physical processes that generate it undergo a significant alteration. The study of upsweep has significantly advanced our understanding of the acoustic signatures of deep-sea geological processes. It has highlighted the complex and often subtle ways in which the Earth's internal forces manifest acoustically in the ocean. Researchers now have a more refined understanding of how magma movement, hydrothermal venting, and tectonic activity can contribute to the deep ocean's ambient soundscape, providing unique insights into these otherwise hidden phenomena. The narrow-band, persistent nature of upsweep in particular has encouraged scientists to look for similar signatures in other tectonically active regions, potentially revealing new, long-term indicators of geological activity beneath the waves. So while upsweep may not be the voice of an unknown creature or a cryptic message from the deep, its persistent hum represents a profound, long-duration drone from the very heart of our restless planet. It is the sound of geological forces, slow and inexorable, continuously shaping the ocean floor, emitting a steady, resonant signal that speaks of magma, flowing water heating, and tectonic plates grinding. Upsweep serves as a powerful reminder that the deep ocean is not merely a passive recipient of sounds, but an active, dynamic acoustic environment where the Earth itself sings groans and hums, with an intensity and persistence that can span decades. It is a testament to the ocean's enduring capacity to produce sounds that, while eventually explained, continue to challenge our initial perceptions and deepen our appreciation for the complex, vibrant, and still mysterious acoustic world beneath the waves, drawing us ever further into its resonant, whispered secrets. The uncatalogued resonances. While the Bloop, Julia, and Upsweep have garnered significant attention, weaving their way into both scientific discourse and popular imagination, they represent but a fraction of the enigmatic acoustic signals that have emerged from the deep ocean's long, patient vigil. Beyond these well-known mysteries, the vast, continuous datasets collected by NOAA's hydrophone networks, and indeed by other global acoustic observatories, contain a wealth of uncatalogued resonances, a chorus of sounds that continue to defy easy explanation. Pushing the boundaries of our current understanding, these are the truly unknown whispers, the spectral groans, and the subtle rhythmic pulses that hint at processes or entities yet to be fully comprehended, inviting us to peer into the deepest, most profound corners of the ocean's enduring sonic enigma. One such intriguing yet largely unexplained category of sounds involves what scientists sometimes refer to as slow-moving events. These are not the abrupt, powerful bursts of an earthquake or the distinct calls of a wail. Instead, they manifest as very low-frequency, long-duration pulses or shifts in the ambient noise floor, often spanning minutes or even hours, slowly evolving in their spectral characteristics. Imagine a colossal, unseen force gradually exerting its influence on the water column, creating subtle yet pervasive pressure fluctuations that ripple outwards over immense distances. These events often lack the distinct, sharp onset of a known geological rupture, or the modulated patterns of biological communication, making their identification and attribution particularly challenging. Scientists theorize these could be related to extremely large-scale, slow-motion movements of deep ocean currents interacting with complex seafloor topography, or perhaps the subtle, continuous grinding of tectonic plates at extremely slow, slip-rates processes that unfold on geological timescales, but can manifest acoustically in unexpected ways. The energy involved would be immense, but spread over such a long duration that the individual acoustic signature becomes a diffused, lingering presence rather than a sharp, identifiable event. Another perplexing set of uncatalogued sounds manifests as highly localized, yet powerful broadband bursts, often occurring in regions not typically associated with known seismic or volcanic activity. These are not the broad, basin-wide detections of the Bloop, but rather intense, short-duration events registered by only a few closely spaced hydrophones, suggesting a relatively confined source. The challenge here lies in their unpredictability and their unique spectral signatures, which often do not perfectly match the established acoustic profiles of known deep-sea phenomena. Could these be the sounds of deep-sea methane seeps, suddenly releasing large volumes of gas from the seafloor, creating turbulent, explosive bursts? Or perhaps the collapse of vast, unseen underwater cave systems, or the dramatic, localized fracturing of deep-sea bedrock under immense stress? The transient nature and specific spectral characteristics of these events suggest unique, perhaps rare, localized processes that are not yet fully understood, their fleeting presence making them particularly difficult to study and attribute definitively. Furthermore, the continuous monitoring of the deep ocean has revealed a fascinating array of rhythmic, almost mechanical-sounding pulses that defy easy biological or geological classification. These are not the irregular clicks of sperm whales or the complex songs of humpbacks, nor the chaotic rumble of tectonic shifts. Instead, they present as highly regular, almost perfectly timed sequences of broadband clicks, or low-frequency thumps, repeating with an uncanny precision that suggests either an astonishingly consistent natural process, or more speculatively, an unknown form of highly organized biological activity. Imagine a colossal, unseen clock ticking in the deep, its rhythmic pulses echoing through the abyssal plain. Scientists have pondered if these could be generated by specific yet undiscovered deep-sea organisms, employing a unique form of echolocation or communication, perhaps on a scale far grander than anything currently known. Or alternatively, could they be related to specific hydroacoustic phenomena, where unique interactions between current seafloor topography and water properties create self-sustaining rhythmic acoustic patterns, a kind of natural deep ocean resonator? The regularity of these pulses is what makes them so profoundly intriguing, challenging our assumptions about the spontaneity of natural sound. The technological challenges of identifying and attributing these uncatalogued resonances are immense. Firstly, the sheer volume of data generated by global hydrophone networks is staggering, requiring sophisticated algorithms and machine learning techniques to sift through the ceaseless torrent of information. Distinguishing a truly novel signal from background noise or from subtle variations of known sources is a monumental task. Secondly, the deep ocean itself is a complex and often unpredictable acoustic medium. Sound waves are affected by temperature, salinity, and pressure, which vary with depth and geographical location, causing signals to refract, reflect, and scatter in intricate ways. This means that a sound emitted from a specific source might arrive at a hydrophone array with a distorted or altered signature, making its precise identification even more challenging. Without visual confirmation or additional sensor data from the source region attributing these sounds remains largely a process of elimination and educated speculation. Moreover, the vast majority of the deep ocean remains utterly unexplored. While advanced mapping techniques have provided a general understanding of seafloor topography, the intricate details of deep-sea geology, the full diversity of abyssal ecosystems, and the precise nature of active geological processes remain largely unknown. It is entirely plausible, even probable, that the deep ocean harbors undiscovered forms of life, entirely new geological phenomena, or unique hydroacoustic interactions that are currently beyond the scope of our scientific models. These uncatalogued resonances therefore serve as tantalizing acoustic clues, faint whispers from these unexplored realms, urging us to continue our journey into the unknown. Consider, for example, the deep ocean's role as a vast natural waveguide. The unique properties of water, particularly the presence of the SOFAR sound fixing and ranging channel, a layer in the ocean where sound travels at its minimum speed, allow low-frequency sounds to propagate with astonishing efficiency over thousands of miles. This means that a relatively modest sound source, if located within or near the SOFAR channel, could potentially be detected across entire ocean basins, its origin still remaining incredibly difficult to pinpoint with precision. The uncatalogued resonances might be echoes of such distant, perhaps even transient phenomena, their true source diluted by the immense distances and the complex acoustic pathways they traverse. The ongoing quest to understand these uncatalogued resonances is a testament to the enduring spirit of scientific inquiry. It requires a multidisciplinary approach combining expertise from oceanography, seismology, marine biology, and acoustic engineering. Researchers are continuously developing more sophisticated signal processing techniques, employing advanced algorithms to extract subtle patterns and anomalies from the noisy background. They are also deploying new generations of deep-sea observatories equipped with not only hydrophones but also temperature sensors. pressure gauges, chemical detectors, and even cameras in an attempt to correlate acoustic signals with other environmental parameters. This integrated approach slowly and meticulously aims to build a more complete picture of the deep ocean's dynamic processes. Ultimately, these uncatalogued resonances are not merely scientific curiosities. They are profound reminders of the ocean's immense, still untapped potential for discovery. They are the acoustic signatures of a world that continues to hold secrets, a realm where the forces of geology, the mysteries of life, and the complex physics of sound converge in ways we are only just beginning to comprehend. Each unexplained hum, each rhythmic pulse, each lingering spectral voice serves as an invitation, a gentle beckoning from the deep, urging us to listen more closely, to delve deeper, and to expand the boundaries of our knowledge, acknowledging that the ocean, in its vast dark embrace, still holds countless wonders and profound enigmas waiting patiently for us to uncover their whispered truths. The journey into the deep ocean's acoustic unknown is far from over. In many ways, it has only just begun. Principles of acoustic analysis. The journey into the ocean's acoustic mysteries, from the titanic roar of the Bloop to the persistent hum of upsweep and the subtle uncatalogued resonances, is fundamentally a journey of decoding. To move beyond mere detection and into true understanding, scientists must employ a sophisticated array of tools and techniques, meticulously dissecting the raw pressure waves captured by hydrophones into meaningful information. This intricate process, known as acoustic analysis, is akin to deciphering a complex multi-layered language where each ripple and vibration carries a hidden message about the deep ocean's geology, its teeming life, and its profound, often enigmatic, physical processes. At the heart of acoustic analysis lies the transformation of an analog sound wave, a continuous variation in pressure into a digital signal that computers can process and manipulate. Imagine the hydrophone as a delicate ear, converting the subtle pushes and pulls of water into an electrical voltage. This continuous voltage waveform is then sampled at incredibly rapid intervals, typically thousands of times per second, and each sample is converted into a numerical value. This digital representation, a string of numbers, is the raw material that scientists then meticulously sculpt and examine, much like an archaeologist carefully brushing away layers of earth to reveal an ancient artifact. One of the most fundamental tools in this decoding process is the spectrogram. Picture a visual representation, a vibrant, multicolored canvas where time stretches horizontally from left to right, like a slow-moving river. Vertically, we ascend through the spectrum of frequencies, from the deep, guttural rumbles of the lowest tones at the bottom to the sharp, piercing whistles of the highest pitches at the top. The intensity of the sound at any given frequency and time is then represented by color or brightness, allowing researchers to visually perceive the intricate patterns, the rise and fall of pitch, and the duration of acoustic events. A blue whale's song might appear as a series of warm, glowing lines, slowly sweeping upwards in frequency, while an earthquake would manifest as a broad, chaotic burst of intense color, spreading across many frequencies simultaneously. The Bloop, for instance, revealed its biological-like quality through its distinct modulated frequency sweep on the spectrogram, a pattern that guided initial hypotheses towards a living source. Beyond the visual interpretation of spectrograms, scientists delve deeper into the mathematical properties of sound. Frequency analysis, often achieved through the powerful mathematical technique of the fast Fourier transform, allows researchers to break down a complex sound into its constituent pure tones, much like separating the individual instruments in an orchestra. This reveals the dominant frequencies within a sound, its harmonics, and its overall spectral shape. A narrow band signal like upsweep would show a distinct concentrated peak at a specific frequency, while a broadband signal like Julia would display energy spread across a wider range. This detailed frequency information is crucial for distinguishing between different types of sources. For example, the precise frequency of a submarine's propeller cavitation can be a key identifier, just as the specific low-frequency hum of a hydrothermal vent might have a unique spectral fingerprint. Temporal analysis, on the other hand, focuses on how a sound evolves over time. This involves examining its duration, its onset and offset characteristics, and any repetitive patterns or modulations. Is the sound impulsive, like a sudden crack? Is it continuous, like a sustained hum? Does it have a regular rhythmic pulse? Or is it chaotic and unpredictable? The duration of Julia, for instance, lasting an astonishing 15 minutes, was a critical temporal characteristic that immediately narrowed down the range of plausible explanations. Similarly, the rhythmic repeating upsweep pattern of the sound named after it was a key temporal feature that allowed its consistent identification over decades. One of the most powerful techniques for pinpointing the source of a sound in the vast ocean is triangulation. Imagine multiple hydrophones strategically placed at different locations across an ocean basin. When a sound is generated, its pressure waves travel outwards, reaching each hydrophone at a slightly different time, depending on the hydrophone's distance from the source. By precisely measuring these minute differences in arrival times and knowing the exact positions of the hydrophones and the speed of sound in water, scientists can calculate the precise location of the sound's origin. This is a complex geometrical problem requiring sophisticated algorithms and accurate environmental data, but it is the fundamental method used to pinpoint the sources of the Bloop, Julia, and upsweep, revealing their geographical coordinates with remarkable precision. The effectiveness of triangulation is directly enhanced by having a greater number of widely distributed hydrophones, as was the case with the sprawling SOSUS network. However, decoding the ocean's language is fraught with inherent challenges. The ocean itself is not a uniform, static medium. The speed of sound in water varies significantly with temperature, pressure, and salinity, creating complex acoustic pathways. These variations can cause sound waves to refract and reflect, bending their paths and potentially distorting their arrival times or spectral characteristics at distant hydrophones. This phenomenon, known as acoustic propagation, requires sophisticated modeling to accurately account for the environment's influence on sound travel. Scientists use detailed oceanographic data, including temperature and salinity profiles, to build complex three-dimensional models of the sound speed field, allowing them to correct for these environmental distortions and improve the accuracy of their source localizations and spectral interpretations. Another significant challenge is the pervasive presence of ambient noise. The deep ocean is rarely truly silent. It is a cacophony of natural sounds: the distant rumble of currents, the crackle of snapping shrimp, the groans of melting ice, the songs of whales, and the ceaseless pitter-patter of rain on the surface. Added to this natural background are anthropogenic sounds: the hum of shipping traffic, the pings of sonar, and the noise from offshore industrial activities. Distinguishing a faint, enigmatic signal from this rich, often overwhelming background noise requires advanced signal processing techniques, including sophisticated filtering, noise reduction algorithms, and statistical analysis to enhance the signal-to-noise ratio and isolate the target sound. Imagine trying to hear a whispered secret in the midst of a bustling marketplace. That is often the challenge faced by acoustic analysts. Furthermore, the limited ground truth in the deep ocean presents a persistent hurdle. Unlike terrestrial environments where a detected sound can often be visually confirmed or correlated with known activities, the deep ocean remains largely unexplored. When a hydrophone array detects an unknown sound, there is rarely a camera nearby to provide visual confirmation or a research vessel to immediately investigate the source. This lack of direct observational data means that attribution often relies heavily on inference comparison with known acoustic signatures and the careful elimination of other possibilities. The vastness and inaccessibility of the deep ocean mean that many acoustic mysteries remain just that, mysteries awaiting future exploration and technological advancements for definitive answers. The principles of acoustic analysis are continuously evolving. Researchers are developing new machine learning algorithms capable of automatically identifying and classifying sounds, sifting through petabytes of data, with a speed and precision far exceeding human capabilities. These AI-driven approaches are learning to recognize subtle patterns and relationships in the data that might escape human ears, potentially uncovering entirely new categories of deep ocean sounds. New types of hydrophones with improved sensitivity and broader frequency response are also being developed, pushing the boundaries of what we can hear in the deep. Ultimately, decoding the ocean's language is a persistent, iterative process of listening, analyzing, hypothesizing, and refining. Each spectrogram, each frequency analysis, each triangulation point adds another layer to our understanding, slowly peeling back the acoustic curtain that shrouds the deep. It is through this meticulous, slow-motion deciphering that the true character of the ocean's enigmatic sounds, from the powerful to the subtle, gradually begins to reveal itself, allowing us to move from mere detection to a deeper appreciation of the complex, vibrant, and still profoundly mysterious acoustic world that lies beneath the waves, guiding us further into its resonant, whispered secrets. Geological rumbles and cryoseismic groans. Earth's own orchestra. Beneath the tranquil surface of the world's oceans, far from the familiar sounds of wind and wave, lies an immense, unseen orchestra, perpetually performing a deep, resonant symphony born from the very restless heart of our planet. This is Earth's own orchestra, a colossal ensemble of geological rumbles and cryoseismic groans, where the slow, inexorable forces that shape our world manifest as powerful, low-frequency sounds echoing through the abyssal depths. Understanding these profound acoustic signatures is crucial, for they form the very bedrock of the ocean's natural soundscape, providing a reference against which all other more enigmatic sounds must be measured and compared. At the core of this geological symphony are the ceaseless movements of Earth's tectonic plates. Imagine colossal, rigid slabs of the planet's outer shell slowly, imperceptibly grinding against one another, pulling apart or colliding with immense force. These movements, though, often measured in mere centimeters per year, generate colossal stresses that, when released, unleash powerful seismic waves. Submarine earthquakes, far more frequent than their terrestrial counterparts due to the vast network of mid-ocean ridges and subduction zones, are primary contributors to the deep ocean's acoustic environment. When the Earth trembles beneath the waves, the sudden rupture of rock sends broad, powerful pressure waves rippling outwards through the water column. These are typically broadband sounds encompassing a wide range of frequencies, from deep infrasonic rumbles that can travel across entire ocean basins to higher frequency tremors that dissipate more quickly. Their spectrograms often show a chaotic, powerful burst of energy a sudden, intense spread of color across the frequency spectrum, followed by a gradual decay as the reverberations diminish. Scientists use these acoustic signatures to map fault lines, monitor seismic activity in remote regions, and even gain insights into the physical properties of the Earth's crust beneath the oceans. Closely related to tectonic activity are the dramatic, fiery events of submarine volcanism. Along the mid-ocean ridges where tectonic plates pull apart molten rock or magma, continuously rises from deep within the Earth to form new oceanic crust. This process is not always silent. Submarine volcanic eruptions hidden beneath miles of water can be immensely powerful, releasing vast amounts of energy in explosive bursts. These eruptions generate distinct acoustic signatures characterized by sudden, intense broadband noise, often accompanied by strong, low-frequency rumbles and the distinct crackle of superheated steam and gases escaping into the cold seawater. Imagine colossal underwater geysers erupting with a deep, guttural roar, their plumes of superheated water and ash rising like ghostly chimneys into the dark abyss. The acoustic analysis of these events allows scientists to monitor active volcanic systems, track the movement of magma, and understand the processes of seafloor spreading, providing invaluable insights into the Earth's dynamic internal workings. Beyond the explosive events, continuous, more subtle geological processes also contribute to the deep ocean's hum. Hydrothermal vents, those fascinating oases of life found along mid-ocean ridges and in tectonically active zones, are perpetual sources of sound. Here, superheated mineral-rich water heated by magma chambers beneath the seafloor streams out from cracks and fissures. The turbulent flow of this incredibly hot water, as it rapidly mixes with the frigid surrounding seawater, generates a continuous, powerful hiss and gurgle. Imagine a giant, unseen boiler perpetually at work, a constant, energetic whisper that fuels the strange chemosynthetic lifeforms congregating around these vibrant, isolated ecosystems. The acoustic signature of hydrothermal vents is typically a broadband, continuous noise, often with distinct peaks at certain frequencies depending on the vent's structure and flow rate. Scientists utilize these acoustic signals to locate new vent fields, monitor their activity, and study the unique ecosystems they support, revealing a vibrant, noisy world thriving in perpetual darkness. Adding to this geological chorus are the more transient yet equally powerful events of submarine landslides. Imagine immense masses of sediment, sometimes kilometers in extent, slowly accumulating on steep continental slopes or abyssal plains. Triggered by earthquakes, gas hydrate dissociation, or simply the relentless force of gravity. These unstable slopes can suddenly give way, sending colossal volumes of material slumping downwards. The movement of billions of tons of sediment and rock, grinding and churning as it slides down a submarine canyon, generates powerful broadband acoustic signals. These sounds are characterized by a gradual onset, a prolonged period of intense chaotic noise, and a slow decay as the material settles. The acoustic signatures of landslides are complex, reflecting the myriad interactions between sediment water and the underlying topography, providing clues about the scale and dynamics of these often destructive but geologically significant events. Moving from the fiery heart of the Earth to its frozen poles, we encounter another powerful and unique component of Earth's orchestra: cryoseismic groans. The immense slow-motion ballet of ice, particularly in the polar regions, generates some of the most powerful and distinctive natural sounds in the ocean. Imagine colossal glaciers, sometimes miles thick, slowly grinding their way towards the sea. As they reach the ocean, immense blocks of ice, some the size of small cities, fracture and break away in dramatic carving events. This sudden, violent release of colossal amounts of stored energy creates thunderous, low-frequency cracks, pops and prolonged, mournful moans that can travel for hundreds, even thousands of miles through the water. These ice quakes are incredibly powerful, often exceeding the acoustic power of even large earthquakes, and their spectral signatures can be surprisingly complex, sometimes mimicking biological vocalizations, as was the case with the Bloop. Beyond the dramatic carving, the continuous movement and interaction of sea ice also contribute to the cryoseismic symphony. Massive ice sheets driven by currents and winds slowly grind against one another, creating a pervasive creaking and groaning soundscape. As large icebergs drift, they can scrape against the seafloor, generating sustained broadband, grounding sounds, much like Julia's lament, a slow, powerful abrasion of ice against rock. The expansion and contraction of ice due to temperature changes also create distinct cracking and popping sounds, a constant background chatter in the frigid waters. Scientists use these cryoseismic groans to monitor the health and dynamics of polar ice sheets, track iceberg movements, and understand the profound impacts of climate change on these sensitive environments. The acoustic data provides a unique continuous window into the otherwise hidden processes of ice melt and movement, offering crucial insights into the planet's changing climate. The ability to distinguish between these various geological and cryoseismic sounds is a cornerstone of deep ocean acoustic analysis. Each type of event possesses a unique acoustic fingerprint, a specific combination of frequency content, temporal characteristics, and amplitude that allows scientists to differentiate it from other sources. For instance, an earthquake will typically have a sharp, impulsive onset and a broadband spectral signature, while an icequake might show a more complex modulated pattern with distinct low-frequency components. A hydrothermal vent will emit a continuous hiss, distinct from the episodic rumble of a submarine volcano. Through meticulous analysis of spectrograms, power spectral densities, and temporal profiles, researchers can piece together the geological story unfolding beneath the waves. These geological rumbles and cryoseismic groans are not just background noise. They are fundamental components of the deep ocean's natural soundscape, shaping the acoustic environment in which marine life evolves and thrives. They are a constant reminder of the immense, powerful, and often unseen forces that are perpetually at work on our planet, sculpting its surface, driving its internal dynamics, and influencing its climate. By decoding Earth's own orchestra, scientists gain invaluable insights into the very processes that make our planet a living, breathing, and profoundly dynamic entity. And it is against this rich, complex, and often powerful backdrop of known geological sounds that the truly unexplained, the uncatalogued resonances continue to emerge, beckoning us further into the heart of the ocean's enduring mystery, inviting us to ponder what other profound secrets our restless Earth might still whisper from its dark, deep embrace. The call of the unseen hypotheses of unknown life. Amidst the grand resonant symphony of Earth's geological rumbles and cryoseismic groans, and beyond the familiar calls of known marine species, there linger certain acoustic anomalies that stubbornly resist categorization. These are the sounds that, even after meticulous analysis, continue to whisper of a possibility that both excites and humbles our scientific understanding, the potential call of unseen, unknown life. For in a world where less than 5% of the deep ocean has been thoroughly explored, the idea that colossal, undiscovered creatures might inhabit its vast, dark expanses remains a compelling, even tantalizing hypothesis, adding a profound layer of biological mystery to the ocean's enigmatic soundscape. The initial allure of the bloop, with its immense power and biological-like spectral signature, was precisely this very possibility. Imagine a sound so potent that it resonated across thousands of miles of ocean, yet possessed a nuanced, modulated quality akin to the vocalizations of a living creature. This combination immediately sparked the imagination of marine biologists and oceanographers, leading to fervent discussions about the potential existence of a truly gigantic, unknown marine animal. The logic was compelling. Larger animals tend to produce lower frequency sounds to communicate over greater distances, and the bloop's ultra-low frequency components, combined with its sheer acoustic power, seem to point towards something of an unprecedented scale, far exceeding even the blue whale, the largest known animal on Earth. The deep ocean, with its crushing pressures, perpetual darkness, and frigid temperatures, has already yielded a surprising array of life forms adapted to these extreme conditions. From the bioluminescent creatures that create their own light in the eternal night, to the colossal giant and colossal squid, once thought to be mythical, now confirmed inhabitants of the deep, the abyssal realm is a testament to life's astonishing adaptability and diversity. Scientists believe that the vast majority of deep-sea species remain undiscovered, hidden within the unexplored trenches, canyons, and abyssal plains. Given this profound lack of knowledge, the idea of a truly immense, deep-dwelling creature, perhaps even a megafauna that rarely, if ever, ventures into shallower, more explored waters, is not entirely beyond the realm of scientific plausibility. Such a creature, if it existed, would likely have evolved unique physiological adaptations, including the ability to generate powerful low-frequency sounds for long-range communication, navigation, or hunting in its vast, dark environment. Consider the requirements for a deep-sea creature to produce sounds like some of the more enigmatic, uncatalogued resonances. It would need specialized acoustic organs, perhaps a highly developed larynx, or a resonant internal structure capable of generating sustained, powerful, and often low-frequency vibrations. The dense medium of water, while efficient for sound propagation, also requires significant energy to set in motion. Therefore, a creature generating sounds detectable across thousands of miles would likely possess a considerable body mass, allowing it to move large volumes of water and create powerful pressure waves. The biological-like characteristic of some of these unexplained sounds, with their modulated frequencies and distinct temporal patterns, often stands in stark contrast to the more chaotic or purely physical sounds generated by geological processes, lending credence to the idea of an organic source. Beyond the hypothetical single colossal creature, another fascinating biological hypothesis centers on the possibility of vast undiscovered supercolonies of smaller yet highly vocal deep-sea organisms. Imagine immense aggregations of crustaceans, fish, or even unknown invertebrate species, each contributing its own small sound, but collectively generating a powerful diffuse acoustic signature that could be mistaken for a single colossal source. Some deep-sea ecosystems, particularly around hydrothermal vents, are known for their astonishing biodiversity and dense populations. If a highly vocal species were to form such a supercolony, its collective acoustic output, especially if synchronized or amplified by unique environmental conditions, could potentially account for some of the more persistent broadband and spatially diffuse enigmatic sounds. However, the sheer acoustic power and long-range detection of events like the Bloop or Julia would still necessitate an extraordinarily dense and vocal aggregation far beyond anything currently observed. The challenges in confirming a biological origin for these unexplained sounds are immense. The primary hurdle is the absence of direct observation. Without visual confirmation or the ability to collect biological samples from the source region, any biological attribution remains purely speculative. The vastness and inaccessibility of the deep ocean mean that deploying remotely operated vehicles, ROVs, or autonomous underwater vehicles, AUVs, to investigate a specific acoustic anomaly is an incredibly complex, time-consuming and expensive endeavor, often akin to finding a needle in an ocean-sized haystack. Even if a vehicle were successfully deployed, the creature might be highly elusive or sensitive to the presence of human technology, retreating into the darkness before it can be observed. Furthermore, our understanding of deep-sea biology, particularly the acoustic capabilities of its inhabitants, is still in its infancy. Many known deep-sea species are silent or produce sounds that are beyond our current detection capabilities. Conversely, there might be species that produce incredibly powerful sounds, yet remain undiscovered due to their rarity, their elusive nature, or their habitat in truly unexplored regions. The biological-like quality of a sound, while suggestive, is not definitive proof of a biological origin, as complex geological processes such as ice fracturing can produce surprisingly similar acoustic signatures, as was eventually determined for the Bloop. The ocean is full of acoustic mimicry, where abiotic forces can sometimes imitate the sounds of life. The scientific community maintains a cautious yet open-minded approach to the hypothesis of unknown life. While the initial excitement surrounding the Bloop as a potential unknown creature has largely given way to a geological explanation, the underlying premise that the deep ocean still harbors profound biological mysteries remains valid. The uncatalogued resonances, those subtle, persistent, or rhythmic pulses that defy easy explanation, continue to fuel this inquiry. Scientists are actively working to develop more sophisticated acoustic analysis techniques, including advanced machine learning algorithms that can better differentiate between subtle biological patterns and complex geological phenomena. They are also advocating for increased exploration of the deep ocean using next-generation submersibles and remote sensing technologies in the hope of eventually correlating acoustic anomalies with direct observations. The enduring allure of the call of the unseen is deeply rooted in our human desire to explore, to discover, and to understand the full extent of life on our own planet. The deep ocean, with its vastness and its profound mysteries, represents one of the last true frontiers of exploration. The possibility that its darkest, deepest chambers might harbor life forms of unimaginable scale or complexity, life that communicates in ways we are only just beginning to perceive through faint acoustic whispers, is a powerful motivator for continued scientific endeavor. These hypotheses, though speculative, remind us of the immense humility required when confronting the unknown, acknowledging that our current catalogue of life and our scientific models are far from complete. They challenge us to keep listening, to keep searching, and to remain open to the astonishing revelations that the deep ocean may yet yield, drawing us ever deeper into its profound, living, and still mysterious embrace. The ocean's enduring mysteries. Even as scientific rigor has slowly, meticulously peeled back the layers of mystery surrounding some of the ocean's most enigmatic acoustic events, providing plausible geological explanations for the Bloop and Julia, and a consistent origin for upsweep, the vast dark waters continue to hold a multitude of secrets. We stand in many respects at the very edge of understanding, gazing into an abyss that still echoes with questions, where the known seamlessly transitions into the unknown, and where the most profound mysteries of our planet patiently await their unraveling. The ocean's enduring enigmas are not simply isolated phenomena, They are constant reminders of the immense humility required when confronting a realm so vast, so ancient, and so profoundly alien to our terrestrial experience. One of the most persistent and challenging mysteries at the edge of our understanding is the profound lack of comprehensive data from the deepest parts of the ocean. While our hydrophone networks have provided invaluable insights into the mid-ocean basins, the extreme depths of the abyssal plains, and more significantly, the ultra-deep trenches such as the Mariana Trench, descending nearly 7 miles below the surface, remain largely acoustically unexplored. Imagine a world where the pressure is so immense that it could instantly crush the most robust, human-made submersibles, a realm of perpetual darkness where temperatures hover just above freezing. Our current hydrophone technologies, while incredibly resilient, often face significant limitations in these extreme environments, making long-term continuous acoustic monitoring incredibly challenging. What sounds might resonate from these ultimate depths? Could there be unique geological processes or forms of life adapted to these pressures that generate acoustic signatures entirely unlike anything we have yet encountered? The absence of data from these regions is not merely a gap in our knowledge. It is a vast, silent canvas where unimaginable acoustic wonders might lie hidden, waiting for a future generation of technology to finally listen. Furthermore, the complex interplay between different acoustic sources presents another layer of enduring mystery. The ocean is not a collection of isolated sounds. It is a dynamic, multi-layered symphony where biological calls, geological rumbles, and anthropogenic noise constantly overlap and interact. Distinguishing a truly novel signal from the background cacophony or from the subtle variations of known sources is a monumental analytical challenge. Imagine trying to identify a single, unique musical note within a colossal dissonant orchestra. The possibility exists that some of the uncatalogued resonances, those subtle whispers and rhythmic pulses, are not entirely new phenomena, but rather complex emergent properties arising from the interaction of multiple known sources, or perhaps a known source behaving in an unexpected way under specific environmental conditions. Deciphering these complex interactions requires not only advanced signal processing, but also a more holistic, integrated understanding of the ocean's physical, chemical, and biological processes, a level of interdisciplinary knowledge that we are only just beginning to achieve. The question of undiscovered biological vocalizations remains a potent, enduring mystery. While the initial excitement around the Bloop as a potential unknown creature has been largely tempered by geological explanations, the sheer vastness of the unexplored deep ocean means that the possibility of undiscovered megafauna, or even highly vocal numerous species, cannot be entirely dismissed. As we discussed, less than 5% of the ocean has been thoroughly explored, and the sheer diversity of life on Earth, even in its most extreme environments, continues to astound us. Could there be a species of whale, perhaps a deep-diving beaked whale, that produces extremely low-frequency calls that our current models struggle to accurately attribute? Or perhaps entirely new phyla of deep-sea invertebrates that communicate through unique acoustic means? The very concept of biological-like acoustic signatures is subjective, and our current understanding of marine bioacoustics, particularly for deep-sea organisms, is far from complete. The ocean's enduring capacity to surprise us with new life forms means that the call of the unseen will always remain a compelling, if speculative, hypothesis. Beyond the specific sounds, the very long-term acoustic trends in the ocean present their own set of profound mysteries. How has the ocean's soundscape changed over geological timescales, and how is it currently being impacted by anthropogenic activities? The continuous records from hydrophone networks, while invaluable, only span a few decades. What did the ocean sound like millions of years ago before the advent of industrial shipping or the pervasive presence of human-generated noise? Understanding these long-term trends is crucial for assessing the health of marine ecosystems and predicting future changes. For instance, some scientists theorize that the overall loudness of the ocean, particularly in the low-frequency bands, has increased significantly over the past century due to human activities. How does this increased noise pollution affect the communication, navigation, and survival of marine life, particularly those species that rely heavily on sound for their existence? These are complex, multifaceted questions that require continuous monitoring, historical data analysis, and sophisticated modeling, pushing the boundaries of our current understanding of ocean acoustics and its ecological implications. The limitations of our current acoustic modeling and propagation capabilities also contribute to the ocean's enduring mysteries. While we have made significant strides in understanding how sound travels through water, accurately modeling its behavior over thousands of miles, through complex three-dimensional ocean environments with varying temperatures, salinities and pressures remains incredibly challenging. Subtle changes in the water column, such as internal waves or mesoscale eddies, can significantly alter sound pathways, causing signals to arrive at hydrophones with unexpected delays or distortions. This means that even a well-understood sound source, if its propagation path is complex, could generate an acoustic signature that appears enigmatic or unlocatable. Improving these models, incorporating more real-time oceanographic data, and developing more sophisticated computational tools are crucial steps towards resolving some of the current acoustic puzzles. Ultimately, the ocean's enduring mysteries, particularly in the realm of acoustics, are not simply about individual unexplained sounds. They are about the vastness of our ignorance and the profound complexity of the natural world. They are a continuous invitation to further exploration, to push the boundaries of technology, and to foster a deeper, more interdisciplinary approach to scientific inquiry. Each solved mystery, each attributed sound opens up new avenues of research and reveals new layers of complexity, ensuring that the ocean will always remain a source of wonder and scientific challenge. The journey of decoding the ocean's language is far from complete. It is an ongoing, infinite quest, one that continues to draw us deeper into the heart of its profound, whispered secrets, reminding us that there is always more to listen for, always more to learn in the vast, dark embrace of the deep. The edge of understanding is not a barrier. It is merely a horizon, constantly receding as we journey further into the ocean's boundless acoustic unknown. The lullaby of the unexplained ocean. As our journey through the ocean's hidden symphony gently begins to draw to a close, a sense of profound scale and enduring mystery settles over the vast, dark waters we have explored. We have listened to the colossal roar of the Bloop, a sound so immense it once hinted at leviathans of unimaginable size, now understood as the thunderous fracturing of colossal ice, a cryoseismic groan from the very edge of our frozen world. We have heard Julia's lingering lament, a sustained, wailing broadband sound now believed to be the slow, grinding abrasion of ancient icebergs against the deep sea floor, a mournful song of geological patience. And we have settled into the persistent hum of upsweep, a deep ocean drone that resonated for decades, understood as the steady, resonant voice of submarine volcanism, the Earth's own internal furnace breathing acoustically into the abyss. Each of these sounds, once utterly enigmatic, has slowly yielded its secrets, revealing the powerful, majestic forces that continuously shape our planet both above and beneath the waves. Yet even with these profound insights, the ocean remains a boundless reservoir of the unknown. Its deepest chambers still echoing with uncatalogued resonances, subtle whispers and rhythmic pulses that defy easy explanation. These are the sounds that continue to challenge our most advanced acoustic analyses, signals that hint at processes or entities yet to be fully comprehended, reminding us that our scientific understanding, vast as it may seem, is but a flickering lamp in the face of the ocean's infinite darkness. Imagine, if you will, the sheer volume of water, the miles of unexplored seafloor, the countless species of marine life yet to be discovered, and the geological processes unfolding on timescales that dwarf human comprehension. Each moment that passes the hydrophones, those patient, tireless ears of humanity continue their silent vigil, recording the ceaseless complex symphony of the deep, a constant flow of data that promises to reveal even more profound mysteries in the years to come, slowly, gently, continuously. The true lullaby of the unexplained ocean, therefore, is not found in a single definitive answer, but in the acceptance of its enduring mystery, in the comforting knowledge that vast, unseen forces are perpetually at work shaping our world, with a rhythm far older and grander than our fleeting human experience. It is the steady, pervasive background hum of the deep, a blending of all these known and unknown sounds that cradles the abyssal realm in a continuous resonant embrace. Picture the slow, inexorable drift of deep ocean currents, their vast, silent rivers flowing across the abyssal plains, creating subtle rhythmic murmurs as they encounter ancient seamounts and deep-sea canyons, a gentle, pervasive swish that speaks of the ocean's ceaseless journey. These are the deep, infrasonic vibrations that permeate the water column, often too low for the human ear to consciously perceive, yet they are always there, a fundamental pulse of the planet itself, a constant underlying thrum that speaks of immense scale and infinite patience. Consider the gentle, persistent creaking and groaning of the Earth's crust, the slow, imperceptible stretch and release of tectonic plates, a continuous whisper of geological movement that, while rarely dramatic, is always present, shaping the very bedrock beneath us. These are the soft, deep shudders of a living planet, forever shifting, forever reshaping its surface, their acoustic signatures forming a fundamental, pervasive layer of the ocean's ambient soundscape. Even the distant, faint crackle of distant ice melting and reforming in the frigid polar waters contributes to this deep-sea lullaby, a subtle, ethereal hiss that travels through the SOFAR channel for thousands of miles, a gentle, almost imperceptible static that reminds us of the planet's vast, interconnected systems, always in motion, always in flux. The ocean in its entirety functions as a colossal breathing entity, its vast body filled with the subtle, continuous movements of water, the slow, rhythmic exhalations of geological activity, and the faint, intricate whispers of its myriad inhabitants. Even as specific, powerful events like the Bloop or Julia capture our attention, it is this pervasive, underlying hum, this constant, gentle resonance that truly defines the deep ocean soundscape. It is a world where sound travels with an unparalleled efficiency, wrapping around every corner, penetrating every depth, a constant, soothing presence that fills the vast, dark chambers where light can never reach. This omnipresent acoustic field, a blend of known geological processes, the distant calls of unseen life, and the subtle, continuous flow of water, creates an environment that is never truly silent, but rather vibrates with a deep, resonant calm. As your own consciousness drifts, carried by the gentle currents of thought, Allow these deep ocean sounds to become a part of your inner landscape. Imagine the immense dark waters stretching out endlessly, a realm where time itself seems to slow, where the world beyond your immediate senses continues its profound, ancient rhythms. The lingering mysteries, the uncatalogued resonances, are not sources of apprehension, but rather invitations to wonder, gentle reminders of the vastness that surrounds us, a world that continues its quiet, powerful existence even as we rest. The deep ocean, with its patient hydrophones still listening, its unseen currents still flowing, and its enigmatic sounds still echoing, becomes a metaphor for the profound, unexplored depths within ourselves, a boundless realm of peace and gentle discovery. Allow the gentle, pervasive hum of the deep ocean, the distant, soft shudders of the earth, and the ethereal whispers of its unseen processes to cradle your mind. Let the sheer scale of these natural phenomena, the slow, inexorable rhythms of our planet, wash over you, a comforting presence in the vastness. The ocean, in its eternal quietude and its ceaseless resonant activity, offers a profound sense of peace, a reminder that even in the deepest darkness there is always a gentle, pervasive sound, a continuous soft vibration that speaks of life, of geological patience, and of the grand unfolding story of our world. This enduring symphony, this deep-sea lullaby, continues its endless performance, a tranquil, resonant presence in the profound depths, even as the world above slows its frantic pace. And so, as we gently drift away from the profound, echoing depths of our planet's mysterious oceans, the whispers of the Bloop, Julia, and upsweep begin to recede, settling into the quiet, soft corners of our minds. We have journeyed through realms where the earth itself hums and groans, and where immense unseen forces sing their ancient songs. Just as the deep ocean holds vast, unexplored chambers, filled with sounds that once defied understanding, so too does the approaching embrace of sleep invite us into its own boundless, unexplored waters, a realm where the conscious mind surrenders its vigil. Here, thoughts and worries can dissolve like faint echoes in the immense, comforting stillness, preparing your spirit for its own unique nightly voyage. Your dreams, like the ocean's deep currents, are ready to carry you now into realms where the known and the unknown gently intertwine, where every sound becomes a part of a tranquil, endless quiet. May the deep, resonant calm of the ocean floor, with its patient, ancient rhythms, cradle your dreams, guiding you into a truly restorative and profoundly peaceful rest. Sleep well, see you again.